Okay, welcome back, everybody. I don't mean to make light of any situation that's going on right now, but um, I decided that we're going to make Fridays tie-dye Friday. Okay, so you can wear your tie-dye if you want. I'm going to wear mine because I'm an old hippie. Um, so let's get started with the third video. I hope everybody is doing well and being safe. Please heed the precautions from health officials and from other people, and take care of yourself, okay? Perhaps we can talk about the whole flattening of the curve that we're trying to accomplish through social distancing, or as I like to call it, and some people have said, physical distancing, because hopefully we can still remain social with the social media tools that we have. Anyway, our last video, we left with this kind of a mess here, looking at sampling distributions, and I just want to review this because it's extremely important. And in fact, I would really like you to get this a little bit closer, I'd really like you to keep this series of graphs in mind. It will help you for sure. I don't want to keep drawing this. Nobody does. And so we're going to put it in symbolic terms when we talk about central limit theorem. But let's just review for a moment here what we did. We started off with a population of 25 scores. Okay, these were the blocks that were in that canvas bag. 25 of them, they each had a number. It had a mean of 14. And of course, it has some standard deviation, right, of some sort. It doesn't matter what that is. We could calculate it, but I'm not going to do that. We'll get to the standard deviation in a minute, okay? Took out samples. We started by taking out samples of 2, okay? Take out 2 blocks, get the average, then put that average on this curve. Then take out another 2 blocks, get the average, put the average on that curve. Take out another 2 blocks, get the average, put the average on that curve. So this ends up being a distribution of sample means. It's the sampling distribution of sample means. For this one, we took out samples of 4. Get a sample of 4, get the average, make 1 block for that sample mean, and put it in on this graph. Take out another sample of 4, get the mean, put that block on here. That is, it represents the means of samples, okay? And finally over here, we had samples of 8. Samples of 8, okay? Take out 8, get the average, plot that. Take out 8, get the average, plot that, okay? I mean, if you can keep that in mind, you'll be really well off when we move forward, okay? Now, we ended up talking about the fact that the means for each of these sampling distributions of means will actually equal the mean of the original population of individual scores. Okay, let me say that again. The means of each of these sampling distributions of sample means will actually equal the mean of the original population of individual scores. Okay, so this was 14. Once we took out 1,000, 10,000, 100,000, a million, it's actually hypothetically an infinite number. This will actually, when we plot all of those samples, will actually give us a mean of 14, the same as what we had here. Likewise, when we have samples of 4, sample 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 of 4, 100,000 times, a million times, when we do that and plot all of those, we'll get a mean of 14. That was the mean of the population of individual blocks that we had. Same with samples of 8. Eventually, it'll create a curve where the mean will be equal to the original population. Okay? That's a fact. I'll show you in a little bit a little toy I have that is quite convincing too. People sometimes don't understand that this is just based strictly on probabilities. It's just a probability. I mean, if you flip a fair coin 100 times, you're going to get close to 50-50. If you flip it 1,000 times, you're going to get really close to 500-500. If you flip it 10,000 times, you're going to get really close to 5,000, and so on and so on. That's just how it works. But I'm going to, I don't want to draw this series of graphs all the time. Plus, there's other sample sizes that we could have put in here. And so what I want to do is capture what we see here. That's why I want you to keep this in mind. Always be thinking about this progression. Okay. I want to capture that in simpler. Oops, let's do this. Getting ahead of myself a little bit here. Okay. I want to capture this in a formula that is meant to simplify things, but it'll only simplify if you can keep in mind that the series of graphs I just showed you. Okay. So then this is called the central limit theorem. It is the building block for what we're going to do when we start doing our really cool stuff related to research. Okay. So we're making that transition from descriptive statistics to inferential, so we can use it for research. Central limit theorem has two parts, okay? One of the things, and I'm going to ask you this on the exam, of course. One of the frustrating things for me sometimes as a teacher is that students will talk about this part or this part, but they're not going to talk about both. Central limit theorem has two components. Let's go through them. First component, let's think about what these symbols mean. This becomes your cheat sheet in a way. I'll give you the formulas. If you know what the symbols mean, you can generate the concept. Okay? This is the mean. It's a mu, symbol for the mean, has a subscript of m. What that's telling me is this is the mean of the distribution of sample means. I'll say that again. When we have our sampling distribution of sample means, where we plotted each of the sample means, 1,000, 10,000, however many, this tells me the overall mean of all the sample means. This is the overall mean of all the sample means. This is the mean for my sampling distribution of sample means. Okay? And what this formula is telling me is that will equal the mean of the individual scores. That is, the population of individual scores that we took the samples from. The mean of any sampling distribution is equal to the mean of the distribution of individual scores from which the sample was taken. The mean of any distribution of sample means will be equal to the mean of the original distribution, that is the individual scores that we took the samples from. Okay? That's where we left off in the last video, but I wanted to review. Here's the second part of the central limit theorem. Two parts. First part, second part. Okay? The second part relates to the variability of the sampling distribution. It relates to the variability of the sampling distribution. And what we noticed from what I just showed you, that series of graphs, what we notice is as we increase the size of our samples, we saw this decrease in the variability of my sampling distribution of sample means. Take your time. As we increased the size of the samples, we saw a decrease in the variability, a decrease in that standard deviation. Okay? So here it is in formula form, and that is, this is the standard deviation, right? Sigma, we've used that symbol before. It's the standard deviation. It tells us about the variability. But here it's subscripted with M. That means it is the variability of the sampling distribution. Okay? It's the variability of the sampling distribution of means. Standard deviation, this is telling us of all those means that we're putting up, those blocks now are M's, means. And so we're going to get the variability. A little bit more complicated here, but let's look at it for a minute. As we increase the size of our samples, we saw the decrease in variability. That's called an inverse relationship, okay? And we can accomplish that relationship by putting n in the denominator here, okay? So as this number increases, the output here will decrease, okay? As this number increases, the output will decrease. That's what we saw in those graphs. Now, it's actually the square root of n instead of just putting n there. There's a mathematical reason for that we don't need to get into. The basic concept there is as we increase the sample size, we see the decrease in variability. Okay? If we start off with a canvas bag that has more variability in it, the sampling distributions are going to tend to be more variable as well. It'll still decrease as we increase our sample sizes. We still have this relationship, but we have to keep in mind that if we start with a larger standard deviation in our canvas bag, we're going to tend to get a larger standard deviation for our sampling distribution. Okay? So we're going to put that on the top. So it's directly related to the standard deviation of my original population. It's inversely related to the sample size. This right here is the mathematical version of looking at that series of graphs. Okay? Try not to disconnect these two things because they're absolutely connected. This is the variability of the sampling distributions. As we increase our sample size, we decrease the variability. Okay? Now, one caution here, because this comes up all the time. When I talk about the size of the sample we're taking out, I'm talking about the size of the sample, the number of, if I have a sample of 4, I'm taking out 4 blocks. Okay? Take out another 4 blocks. Take out another 4, get the means for those. Okay? Take out another 4, take out another 4, take out another 4 blocks, take out another 4 blocks. I'm going to do that 10,000 times. Look at my head. It's kind of weird. It's the size of each of those samples that I'm talking about here. It is not the number of samples. Okay? It's the size of the sample, not the number of samples. This is one part on an exam, and of course I'm going to ask you this, that people often will make a mistake. They'll say, well, the more samples that you take out, the smaller the standard deviation. That is incorrect. Everybody hear that? The more samples I take out, the smaller the standard deviation. That is incorrect. It is the larger the samples, the smaller the standard deviation. So if instead of samples of 4, I take out samples of 15, I'm going to have smaller standard deviation with those samples of 15. My assumption is that you're taking out 10,000, 100,000, a million, an infinite number. That's why I keep saying that. It's not the number of samples, it's the size of each of the samples. 4, or 8, or 15. That's what I'm talking about. We're assuming that we're taking out, for the sake of developing this theorem that we're taking out 100,000, a million, so on and so forth, right? So it's not the number of samples, it's the size of the sample, okay? I can talk about the size of your car, or I can talk about the number of cars that you have, right? Those are two different things. In this case, I'm talking about the size of the sample. There's 4 people in the sample. There's 20 people in the sample. Not the number of samples. We just assume that's a lot. Okay? So, central limit theorem has 2 components. Something that tells you about the mean for my sampling distribution. Something that tells me about the standard deviation for my sampling distribution. Okay? Let's go back to the curve here, and I want you to see how this matches up with the curve. Keep this in mind, and it'll help you understand this, right? My standard deviation is getting smaller as I increase my sample size. Not the number of samples. I'm going to have 1,000 in each of these distributions, but it's the size of the samples that I'm talking about. Mean will be the same as the mean here. The mean of the sampling distribution of sample means will be the same as my original, okay? Overall. And then my standard deviation will vary, okay? Let's see what I have here, here. Let me go back. Okay. I want to show you a little toy. And it's very cool. I hope that it will, hope we can see it here. Okay. This is called a quincunx. Quincunx. It's pretty weird. And let me explain this to you. So down here is a bunch of ball bearings. Okay, I'm holding this upside down. I'm going to turn this right side up. All these ball bearings are going to fall down into this area. And there are bins here that will capture those ball bearings. So let me show you how this works. Oh boy. Okay, here we go. What do you see there? A nice normal curve, okay? A nice normal curve. And most of the ball bearings are in the center, okay? Let me go back. There's 256 ball bearings in there. I'm going to do it again, and we'll see a nice normal curve. Let's do it again, and we'll see once again a nice normal curve. Okay. Let's do it again, and we'll see a nice normal curve. Okay. Now this is an interesting toy, and you might be thinking to yourself, what the hell does this have to do with anything, right? Well, the 256 ball bearings are up here. And by the way, you can get demonstrations of this on the internet all over the place. Quincunx. Okay? But this is, again, a very low-tech version, and I like low-tech versions because there's nothing fancy about this. Nobody's programmed this. The ball bearings get to do whatever the hell they want, and I like that, okay? And what happens is the ball bearing comes down through here, and at this point, it can go either left or right. Should be fairly random. Then it goes down to the next step, and it can go left or right again. The next step can go left or right. Next step go left and right. Next step go left and right, so on and so forth. What this is showing you is it's actually a sampling distribution because there's 256 of these little ball bearings, and each one of them can go left or right at all of those different choice points. And what this is showing you is that most of the ball bearings, by the way, there's, let's see, 1, 2, 3, 4, 5, 6, 7, 8 choice points. This is always going to be, oops, did I say always? Always, yes, for all intents and purposes, always going to be the bin with the highest number of ball bearings, because it represents the ball bearing that went left and right an equal number of times. Okay. Out here is a ball bearing that went to the left every time. Here's to the right every time, and so on and so forth. Very rare to get a ball bearing that went to the right every time or to the left every time. Okay, and here is 7 out of 8 in one direction. Here's 6 out of 8 in one direction, 5 out of 8 in one direction, 4 out of 8 in one direction. Okay, let's do it again. And you see the same thing every time, okay? Is it possible for all the ball bearings to go to this bin? It absolutely is possible. It absolutely is possible. I would bet $1,000 that if we did this 1,000 times, you'd never see all the ball bearings in, or a majority of ball bearings here. And anybody wants to take me up on that, we can meet up in the fall. And I'll win my $1,000. That'd be good. This sort of represents the fact that we tend to, based on probabilities, the most probable thing tends to happen, and that is that we get ball bearings in here. And the more, the larger our sample size, the more we expect things to get in the middle. Okay, the larger our sample size, the more we expect to get things that look like they're average. Okay, so this relates to central limit theorem. Central limit theorem. Okay. Now, let me go. Give me just 1 minute here. Because I want to show you then. So if we start with a distribution that looks like this, okay, these are x values. Once we start taking samples, I'm just cleaning up what we did before. We start seeing something like this. These will all be the same mean. Oops. But remember, these are sample means. Okay. And we have our equations for the central limit theorem. Okay. We see that as we increase the sample size, those samples come inward. Inward to what? Inward to this point. We see that the variability gets smaller and smaller, right? Relative to this. This has, and it's given by, we can figure out the actual numbers, and we will momentarily, okay? We can figure out the actual numbers, but using central limit theorem formulas. But this actually has a name, what's going on, and this is called regression to the mean. Regression to the mean. That is, these numbers are regressing. They're coming inward to the mean value. Okay? When we take samples, we tend to see these numbers come inward. There's less variability, so there's more consistency. Okay? But this regression to the mean, you probably have some kind of gut feeling about it because I'll use a sports analogy again. Let's think about like who's the best basketball player these days on the NBA. I don't know. Maybe it's LeBron James, right? Maybe it's who's the new guy? Zion. I forget his name. Let's just go with LeBron James, right? The weird thing with LeBron James, he's a very, very good basketball player. In fact, if we look at individual basketball players, I put LeBron James out here. I mean, he's really good, really, really good, okay? Many standard deviations away from the mean. The problem for LeBron James is he's got to play with 4 other guys. On the NBA basketball team, there's 5 people. And so, in a way, we have to think about a sample of 5. There's 5 players. Well, once LeBron James gets to in a team and he has to play with 4 other people, the average for the team can never be as good as LeBron James because he's way out here. He's like that 18 in our population and canvas bag. Remember, the 18 was the most extreme score. As soon as we paired 18 with something else, we saw that the average for that sample came in. As soon as LeBron James gets paired with 4 other guys playing basketball, then the team average cannot be as good as LeBron James because he's the best. So, let's just say this is samples of 5, like a basketball team. So here's LeBron James here, but when we put him with 4 other people, the average comes closer to whatever the average for the NBA is. Okay? This is why, folks, it's much more difficult to get a superstar team than it is to get a superstar player. Okay? There's lots of superstar individuals. As soon as they have to start playing with a team, the team average is going to come closer to the overall NBA average. Okay? I mean, LeBron James is going to bring it out a little bit, but in general, they're going to be closer to the average. This is always bad news for the best player in the team because they have to be paired with someone else. It's great news for the worst player in the NBA. The worst player in the NBA, I mean, there is a worst player. Nobody knows his name. Let's just call him Jack, okay? So Jack's the worst player in the NBA. Just a little bit better than me. I'm just kidding. He's the worst player in the NBA. But Jack plays with 4 other players. And so the team is never going to be as bad as Jack. Jack's going to bring them down. But the team is going to be closer to the NBA average than Jack is. Think about Jack as that number 10 in our distribution that we had in the canvas bag. It's called regression to the mean, regression to the mean. Okay? If you've worked on a group project at college, some of the better students who work on group projects hate them. Because why? Because you always got to do the work for other people, right? You're the best person in this group that you're working with. And that group is never going to be as good as you by yourself. And if the teacher grades you as a group, it kind of sucks for the best students. Group work, by the way, is awesome for students who aren't good. That is, who are, lazy, who don't have the background, who, aren't motivated to do the work, so on and so forth. Group work is great for them, right? Because the group is never going to be as bad as they are individually. Regression to the mean, regression to the mean, okay? You're going, if you're playing any kind of sports, whatever it is, you can have a really good game, best game you ever had. But when I look at your season average, the season average is never going to be as good as your best game, okay? If we go back to bowling, just because I know something about bowling, I could have the best game I've ever had, 230 bowling. That's pretty good. I've never done it, okay? Well, I might have 230, but if you look at my season average, it's probably going to be still 155, because once you start adding other scores to it, that is increasing the size of the sample, then things are going to be closer to my bowling average. That sucks if I have a really good game. But it's not so bad if I have a really bad game. If I bowl 84 one game, oh my God. That's okay, because my average for the season, based on, let's say 60 games, my average is never going to be as bad as my worst game. We get this regression to the mean, regression to the mean, okay? Sometimes people call this the law of large numbers. I guess that's okay. The book may even talk about that. I'm not sure. Regression to the mean is much nicer. Go back to my central limit theorem. Go back to the central limit theorem. And here it is again. The larger the sample size, the smaller this is going to be. Okay? The smaller the variability. Okay? So, how are we going to use this? In our research? Or, this is a very important concept, but how does this play out when we're doing work? Well, let's look at our reaction time curve. This is what we did the last week of classes that we're in the classroom. And by the way, I miss it. I miss seeing you guys. I hope you're okay. It's our nice little Monday, Wednesday, Friday meeting. It's the course I enjoy the most. Anyway, let's go back to our reaction time. Look at this a little bit closer, perhaps. This is the curve that we talked about. Reaction time, right? When people come in, they're sitting at the computer, and I'm going to tell them to hit the space bar as soon as they see the letter X, and all of that stuff. Hopefully you remember that. And I said, well, what if the mean was 258? It's 258 milliseconds. Remember? Okay. With a standard deviation of 27. And then we could start looking at people's score. We talked about Bob, right? And here's Bob out here. Bob had a reaction time of what, 333 or something like that, right? And we said, gee, is Bob weird? Well, we're gonna figure out if Bob's weird by looking at Bob's z-score. 333 minus 258 divided by 27. Okay, you guys remember this? And what was Bob's z-score? I don't have my calculator right now. Let's calculate that. Hey, you guys can do it. But what we found was that Bob was way out here. And we said, listen, Bob is weird, right? Because Bob was beyond this was the last question on your exam, right? I said, how do statisticians define weird? And most of you got that. Some of you didn't because you weren't paying attention right at the end of class. We said anything that's outside of the middle 95% is going to be deemed as weird. And Bob was out there, so he was weird. Now Bob might say, hey, wait a minute, I wasn't paying attention, I didn't understand the directions, and really not that slow, and give me another chance. What Bob is saying here is that he wants to give us a sample larger than 1, right? We saw 1 of Bob's scores. It's 333 milliseconds. What he's pleading, he says, listen, that doesn't represent my reaction time. What Bob is saying is, he's got a canvas bag of reaction times, right? There's a population. What's Bob's real reaction time? What are we trying to do? We're trying to infer what Bob's reaction time is. And I hope you know, so we're putting all of this together, you guys. This is not separate stuff. We're putting it all together, So Bob is like, why don't you take out a sample? Now, we're not going into Bob's head with our fingers and pulling out reaction times, but I'm going to say, all right, so let's do this. Let's let Bob do a sample of 3. Let's do 3 trials with Bob. Why would I want to do that? Well, I want to do that because I want to know what Bob's reaction time is. Of course, Bob is motivated because he says, I'm not that slow. Give me another chance. All right. So what is Bob's underlying reaction time? What I'm asking is something equivalent to that canvas bag. Bob has reaction times, and I want to make a guess about what that is. I want to infer what his reaction time is. With just one guess, a trial of 1, I'm going to not be very confident that I know what Bob's reaction time is. Okay? This is equivalent to what I talked about in the other video. I would never make any kind of a judgment about how well a student's doing based on 1 exam, because things happen, right? It may not be representative. But remember, it may not be representative because it's lower than it should be. It may not be representative because it's higher than it should be. That's always a possibility, okay? It's both directions. Regression to the mean means this, coming into the mean. It doesn't mean going this way or going that way, right? Same thing with my golf scores, bowling scores, so on and so forth. But here's the deal. Let's say this is normal reaction time. This is how people react. I'm giving you this as a given, okay? Suppose that the population of reaction time is 258 with a standard deviation of 27, okay? We're going to soon get away from me giving you that information, but at this point I've given it to you. So what I want to say is, okay, let's give Bob 3 chances, because I want to know what Bob's reaction time is. Bob wants us to understand his population. So we're going to give him 3 trials at the computer. So I'm no longer going to be comparing Bob's individual score, right? This is an X, that's an X value. I'm no longer going to be comparing Bob's X score to the X scores, that is individual scores for the normal population. What I want to do is get a mean for Bob. That mean is going to be based on 3 trials. So I'm going to get 3 trials from Bob. I'm going to take the average. That is going to end up being M, right? The sample average. And now I want to compare that to the normal population. What I have to do then is I need to convert the normal population into samples of n equal 3. I'm going to say this again, right? If I'm going to get an average for 3 trials for Bob, what I want to do then is compare that to what normal people look like when they have trials of 3. Bob's average for 3 compared to what normal people look like when I give them 3 trials. Everybody with me? This is like comparing aardvarks and aardvarks, right? I don't want to compare Bob's average of 3 back over here to individual scores. I want to compare Bob's average of 3 to what samples of 3 look like. Okay? Let's give Bob 3 trials, get the average, then we'll make a new assessment. But I think that's a good place to stop, because Bob's not even here. Bob? No, he'll come back. We're gonna let Bob do 3 trials. We're gonna get the average. Instead of comparing it to individual scores, we're gonna compare Bob's 3 trials to what people would look like if they did 3 trials. We're going to use the central limit theorem to figure out what this looks like. We know, right? Individual scores, samples of 3. These are all the different samples of 3, all the different samples of 3, all the different samples of 3. Okay? All the different samples of 3. We're going to see how Bob compares to that. We know what this graph looks like. How do we know? From the central limit theorem. What does this graph look like? It will have a mean of 258. How do we know that? Central limit theorem. The mean of the sampling distribution is equal to the mean of the original. Here's the original. Here's the sampling distribution. I know that this is what it will look like. Okay, how do I know that? Central limit theorem. You'll have this on the exam. Use it. It's a tool. I know that this distribution is going to be less variable. How much less variable? Central limit theorem. This is what it's going to look like. Right here, folks. Individual scores, 27 for the standard deviation. Samples of 3 will look like this. 27 divided by the square root of 3. That's what this distribution will look like. Let me see that all right. Okay. 27 divided by the square root of 3. Why don't you calculate that? And we'll start from there on the next installation of Specht Stats Online. Again, email me if you have questions or trouble seeing this or anything. Email me if you, if you have any concerns. Again, hopefully this is making sense. The good news is you can look at these videos as many times as you want. That's really nice. But please take notes too. That will absolutely help you with this stuff. Read the book. There are other resources online for central limit theorem. You can let me know how good they are. I'm hoping that this was clear for you. Remember, increasing the size of the sample will decrease the variability. That will give me a better guess about what's going on. We'll talk about that next time. See you. Take care.